One of the things I want to mention to you is that the special, excuse me, not special study group, the SI schedule is in the process of formation. Now we've got an online session scheduled for tomorrow, Wednesday, from 4:40 till 5:30 p.m. And the location for that is actually going to be, the link for it is in Web Courses. It's an online SI session. Every lecture that we have is going to have the introductory slide, or the initial slide, looking something like this. We'll have the outline of each topic, the basic outline of the lecture, and then we'll have the SI schedule. Although it's under construction right now, we'll eventually have all the days and locations and times filled in. Hopefully by Thursday we'll have it all worked out. And you'll be able to see that every day. And we'll probably have a quotation of the day once I get activated with that for September. Question? Maria says that there's SI today. When?
From 3 to 3:50 in
3 to 3:50 this afternoon.
Yeah, from 3 to 3:50 on Classroom Building 1, Room 122.
Classroom Building 1, Room 122, from 3 to 3:50. So I'll put in all those times right here on the opening slide every time. Okay, a couple of the things I want to get to, this and that, before we get down to some physics activity. Homework 1 is going to go active for us today right after class. And so I think 1:30 is when it's set to go active. Maria, did you look at it already? Okay, so Maria's taking a look at it. So if you do go to SI this afternoon, you can talk about homework 1. And it's not too bodacious, it's just 4 exercises. And we'll have some big ones coming up. But this first one, calculating some speeds and distances and things like that, not too harsh. And it is going to be due on Thursday at the beginning of lecture. And I believe that for this class, I have it set to 12:01 p.m. Be ready for that every time. I'll give you homework 2 probably on Thursday, and it will be due on Tuesday. And I plan to do my homeworks a little bit differently this semester, making the Tuesday assignments a little bit smaller and the Thursday assignments a little bit bigger to accommodate, or to be accommodated into the shorter time interval between Tuesday and Thursday lecture compared to from Thursday to Tuesday. That's another 5 days. So Thursday assignments will be bigger, but they're always due at the beginning of lecture. Okay, another announcement I want to go over. iClicker is still driving me bonanza. It is not working right. And I'm a little bit ticked off. Well, I'm not ticked off at you guys. I'm ticked off at the iClicker company. I'm ready to, put the blocks to them. But what we're going to do is keep trying to register. And I know some of you have registered, but it's not working consistently and it's not updating for beans. Right now I've got about 150 students out of 600, and so there's a lot of you, I think, that have tried to register and haven't. You're not showing up on the roster, and I don't know why. And in addition, there are some students from like last fall that are still on my roster. I have no idea. But I've got it set to ignore all of them, so that's not a problem. So I'm going to keep synchronizing, and the idea of giving you bonus points for early registration of your iClicker is still an idea, but I have no idea how I'm going to make it work at this stage. But I'm not going to make it work in a way that is negative. Bonus points are always positive. They never hurt. They can only help you. And apparently the big shot, I was talking to one of the big shots at iClicker.com, and he was actually telling me, well, you could do it, you could set it up yourself, and he was giving me this email about how to do it and stuff, and I'm like, no, I want you guys to set it up so that it works instead of malfunctioning. It's ticking me off. I have to ask something, tell something to Caroline. Hold on a second. Caroline, I want you to take notes today as well. So can you sit in the front row until I'm ready for the, and just take really brief notes. Actually, look at what Darian did on the stream. Okay. Caroline is going to be typing notes, also student questions into the Twitter feed, Brainwave777X. She and Darian are part of that team now. This is what it looks like, just kind of a bunch of pictures, and this is, I don't know, sometime last night. It's now a little bit further along, and so we're going to be typing this stuff in real time in class. So as I'm up here blabbing my big mouth about physics and stuff, Caroline's going to be taking notes, so you can be looking at Twitter, and hopefully it'll help you take notes. Also, in the topic of taking notes, hopefully the Twitter thing will be helpful, but what I know is helpful is the YouTube. We record each lecture, we render it to digital video, QuickTime, and then we upload that into YouTube, and you can go and look at it as many times as you want. And what that, I hope, will help you to do is listen more in lecture and don't write down as much. So write down the main headlines in your notes and then listen to me more. And because you're always trying to, taking notes, and you miss something that the instructor says, and then you got, you're lost. But what you can do is take basic notes, like the basic headings, and then listen, and then go back and look at the YouTube and fill in the details from the YouTubes. Because all these outlines and stuff, they're all in YouTube. It's not just me blazing up my big mouth. It's all the notes, all the diagrams, all the equations, and my narration thereof. So it can really help you learn better in lecture, and then extremely learn better as you study after lecture and get ready for each midterm. All right, another thing I want to talk about is tropical disturbance time. Is it a tropical storm yet? Did they upgrade it yet? Anyway, supposedly it's going to be a tropical storm, and it's going to be blazing through here in a few days. So Thursday, you may have to bring a rowboat to school if you want to get home. But hopefully it won't be too bad. Now, one of the things that you hear about when you're listening to the Weather Channel or Channel 9 Eyewitness News, the weather guy will talk about the central pressure in millibars. Now, that is a topic for us this semester. So make a little side note to yourself, a sneak preview. Yeah, we're going to be talking about this. Not today, but we're going to be talking about it. And hopefully I certainly hope, I pray that we do not have any hurricanes hitting Florida. And I hope everybody here agrees with that. We need some rain, but we don't need hurricanes. But we'll be talking about central pressure in hurricanes. A hurricane is a big heat engine. A lot of it runs on the basis of convection. Now, another big convection system, not as big, is a thunderstorm. That's warm air vapor rising through the atmosphere in a convection process, and then when it gets up to a certain altitude, it starts to condense and form a cloud, little droplets of water. We're going to be talking about that. And a hurricane or a tropical storm is a huge convection system. Matter of fact, When a tropical storm forms an eye and becomes a hurricane, that is when it really does mega convection. So it's kind of a cool thing. Another thing that hurricanes do, tropical storms as well, the vapor-liquid phase transition. Anybody know what that is in a hurricane? Vapor-liquid phase transition? This kind of pretty technical. Vapor-liquid. Nobody's ever experienced a vapor-liquid phase transition, I guess. Wrong. You've all experienced it. It's rain. Rain. Yeah, condensation. And, you know, you get buckets of rain, not buckets, I mean mega buckets of rain out of a hurricane. So we'll be talking about that. Yeah, another few weeks. Supplemental instruction schedule. As I mentioned, it's shaping up. Now, the Wednesday session, I guess every week, is going to be online. That's tomorrow. Actually, you're going to have another earlier. Okay, so there's two. There's a regular session and an online session on Wednesday. In web courses, you'll find the URL, and all you have to do is have a web browser. Now, it helps if you're in UCF Adobe Connect to use your earbuds for your phone, or if you have like a USB headset, you know, for gaming or stuff, you can use that. And it really helps to be able to talk to Maria. And just so you know, I use the same software system, Adobe Connect, with my physical science online section for when we have office hours about every week. And it works really good. So if you really want to have a good online session, get some earbuds or a USB headset or something like that, and it'll really. If you use the built-in microphone, it's not very good because you get all kinds of echoes and stuff. It's not very good. But earbuds, very good. The password is Opal. The URL that you have to click on is going to be in web courses. Regular sessions, TBA, and already Maria's told me that we've got one today. So keep an eye. I'll be having it up on the very first slide of every day. And also, there's a SI schedule page in web courses. One more thing I forgot to mention in the morning lecture is we have office hours tomorrow from 11 a.m. to 1 p.m. in the Physical Sciences Building, room 158, right next to the main entrance. And you could, anything you want to talk about, just come and, if you can come for 15 minutes and then you have to bolt, that's fine. It's just drop in, and if you have a question, I'll talk to you about it. But if you don't have any questions, you know, I bring stuff to do. I've always got office work to do, grading papers or what have you. But the agenda is yours, and so you can bring whatever question that you want to office hours. Any questions about SI or office hours? Yes. Today's session is a regular classroom. It's not online. But it's going to be the same password for every online Adobe Connect session. Right? Yeah, it's always Opal. Yeah. Yeah, so the URL and the password will always be the same. And just look in web courses, you'll see it. Okay. And it works good. You know, all you got to have is a good browser and some earbuds and stuff, and you'll be good. You'll see how it works. It's nice. Another question. Yeah, it's all right. All right, let's keep going. Let's get back to physics. Last time we were talking about Galileo and his conviction that the universe is not random and that actually it's comprehensible. And he compared it to a book, the Grand Book of Nature, that it's written in a mathematical language. And a language that's made up of triangles and circles and rectangles and stuff. We're going to be starting to put that together today, actually. It's going to be kind of cool. Now, his whole program of study is what we call the physical sciences or science itself. He's the guy that started it with this conviction that sentences could be written about what we see. Sentences that have a mathematical language, and of course English and Italian, whatever language you're writing in, and that those sentences could be tested for truth. His whole, there's nothing to do there's nothing in this world to do except do things and seek that which is true. I mean, who wants to seek for a lie? Your whole being is oriented to that. And there's a lot of different ways of finding the truth and seeking the truth and determining what is true. And this is the way that Galileo developed to develop truths that are measurable and comprehensible about the physical world. And in that whole enterprise, we are like students in his school. And I'm going to bring up one more concept. It's not in the notes, but I'll just give this to you verbally. And it has to do with what I just said about finding the truth and the sign of the truth. Galileo said if you're going to make a claim in science, you've got to be able to back it up with, it's got to have some kind of a mathematical structure, because that's the language that the great book of nature is written in. All right? That was, you can think of that as one of his rules of how the scientific enterprise works, and that if you fulfill that rule, if it's observable, if it's measurable, if you can repeat it in the lab, if anybody can repeat it in the lab, if they have the right equipment, then yeah, it's reliable. You can depend on it. It's true. Now, I want to compare that to another area completely different, but one in which the rules of truth and untruth are equally important, and that is a court of law. And then you've probably all watched like Law and Order, or some show like that where they have a trial and they got crooks and they're trying to prove them innocent beyond a shadow of a doubt, or they're trying to convict them, and so on and so forth. And one of the things that if you actually are an attorney and you're in a real courtroom, there are rules of evidence. So make a note of that. Rules of evidence. Court of law, rules of evidence. And there's one that I really like. It's a federal rule of evidence. And they probably have similar rules for the state of Florida, but I know the federal rule of evidence, and it's called this: admission against interest. Admission against interest. And what that means is, if a defendant makes a statement, a sworn statement, that is against his interest, in other words, it's going to cost him money, or it's going to cost him time in prison. If it puts him in jeopardy of prosecution, the rule of evidence is that an admission against interest is assumed to be true. All right? That's a rule of evidence. The admission against interest is assumed to be true. Another one, a deathbed confession. Deathbed confession is assumed to be true in a court of law, because, if you're on your deathbed, what do you need to lie about? So that one, now it's not an ironclad rule, but like the admission against interest, but deathbed confession, that's another. So in a court of law, there's the two different ways of finding that which is true. Scientific things, talking about the physical world. That was applause, right? Court of law, legal truths, is the crook guilty or not? two different ways, two different modes, two sets of criteria for discerning that which is true, that you have an interest in. Here's another one. Poetry. You guys are probably, most of you, too young to understand this whole idea of writing a love letter. It's this thing where you take paper and a pen and you write, something lovely to someone that you love, and hopefully they'll receive it, and it'll be true. But the criterion for truth in a love poem, a love letter, is way different than a court of law and then a scientific laboratory. But it's still something, isn't that what everybody's looking for? Their true love. You don't want to find, that's something that you seek that is true, that's solid and reliable. And one of the ways that you find that is through poetry. Now, let me bring this point up. That Galileo, the guy that we're focused on in this class, to whom we are students, he invented, or he developed, this entire scientific mode of finding and making statements that are true. And that is like being the first guy that invented laws. Who is the guy that invented laws? I don't know if anybody ever knows that. It's also the same as the guy that invented poetry. Whoa! Would that be cool to know? Who's the guy that first wrote poetry? And it's greater than William Shakespeare. William Shakespeare wrote poetry, but he didn't invent it. Who's the guy that invented? And here's another one: music. Who's the guy that invented music? Oh my goodness! Can you imagine the guy that invented music? Oh man! And so that's what Galileo is like. He's one of these guys, we don't know who invented music. We don't know who invented poetry. We don't know who invented the law. Although kind of we do in America. We know who wrote the Constitution. The Constitutional Convention and Declaration of Independence, Thomas Jefferson and all those cats, Ben Franklin. But I mean, the very first law, who was that? We don't really know. But we know it is for science. It's Galileo. It's kind of cool. And so we're his students. And here's another student of his, very famous student. Student number one. The student has become the master, Sir Isaac Newton. And you can think of his famous work, the mathematical principles of natural philosophy, as being a study guide. He was studying under Galileo, and he followed Galileo, and he developed his own study guide called the Principia. In Latin, Principia, in English, the mathematical principles of natural philosophies. And this is from the introduction to it. All the difficulty of philosophy, which was his word for physics, physical science, seems to consist in this: from the phenomena of motions to investigate the forces of nature, and then from these forces to demonstrate the other phenomena. Now that's a famous sentence of his from the introduction to his most famous book, the Principia, the mathematical principles of natural philosophy. And the idea of philosophy in his day was the word that we now, is the idea that we now use for physics, or we use the word physics for the same idea that he used the word philosophy. Now, other phenomena, this is what he was thinking about, comets and stuff. Nobody, in Newton's day, they had no idea what comets were about until he developed the three laws of motion and his theory of universal gravitation. And then, by God, they got it. They figured out what they were doing. They nailed them. They got them. Ultra reliable. And NASA's been using his laws of motion for spacecraft, planets, stars, you name it. I mean, it's a lockdown. I mean, stone cold lock. And so that's what he was thinking about. Now, what we're going to be thinking about this semester is the phenomena of motions. Excuse me, the first part of the semester, until about lecture 7 and then exam 1 in lecture 8. All right? And so you know, reading-wise, this is going to take us through chapter 3. We're in chapter 1 now, and we're going to finish in chapter 3 and a little bit, first few paragraphs of chapter 4 about skateboarders, and then we're going to have exam 1. And so we're students of Galileo, and we're using Sir Isaac Newton's study guide. And the first part of his study guide, phenomena of motions. So now what we're going to do is do a demonstration of motion. And let me turn the lights on. And I'm going to ask for some volunteers from the audience who would like some free money. Okay, come on up. Okay, come on up. Do it.
I didn't know you.
Just 2. I only have $2. And in fact, I usually do it with $5 bills. But and so here's the deal. This is a demonstration of Freefall, and what the student is going to do. I'm going to hold this dollar bill up in the air like this, and then I'm going to let it drop. And the student has to grab it. And if they can grab it, they can have it. Now, usually I do it with a $5 bill, but I only have $1 bills. But $100 bills are fine. Okay. Right? And we're going to see if these guys can grab it. And we'll start with you. Now, what is your first name?
Carly.
Carly. Okay, now, Carly, are you righty or lefty?
Righty.
Okay. So I want you to stand over here. Okay. And what I want you to do is put your arm on the table like this, so that your wrist is extending out from the edge of the table. Just like that. Now, she's going to have her hand, you can sit on the chair. Okay. What's your name?
Sam.
Sam. Good job, Sam. I'll sit in the chair over there. Okay, Carly is, now I want you to verify, this looks like a regular dollar bill, right?
Dollar bill.
No, go ahead and touch it. You can practice grabbing it,
Just grabbing it.
And we're going to, and it's just free fall, it's nothing fancy. But she has to have her hand at a set altitude above the floor. Right? So, anybody can catch it. But if your hand is here, and if I put the dollar bill right above your hand, about like this, and drop it, that's not easy. So that's the...
You look worried.
Carly?
I think you're worried.
I'm not worried. I have no worries at all. But I want you to, now, hold your hand about like this, okay? About like that, okay? And I wish this were a little crispier, but it's a little bit, okay, go ahead and grab it. So you can do it. So it's a grabbable dollar bill, all right? Now the thing about it is, when I do this, she missed it. Did you miss it? All right. Let's try. Should I give her another shot? Let's do it. Let's see, Carly. Carly, now don't get nervous.
Totally chill.
Okay, because the thing about this is if you go like, no, I didn't let go of it. If it goes down here, what happened one time, I let it go and it went like this on top of her hand.
There you go.
And I had to give the dollar. It was a $5 bill. Goodness gracious. Okay, so this is the thing that we're going to do. We're going to.
I'm honing in on it.
Well, I don't know. You're high-fiving me.
I get a high five from you.
Thanks, Sammy. How's my butt swing? No, come on up.
He's got $2.
You're good, Carl. Woo! You're the second student. Usually, I must be losing my touch. Because
You're losing your grip.
I'm losing my mental grip. Okay, are you lefty or righty?
I'm righty.
Okay, do the same thing as Carly.
All right.
Let's see if I have a dollar bill over here. Here it is. Okay. Right now, I want you to verify regular dollar. See, these aren't really crispy. You know what it is? If they're crispy, they'll go straight down. But this one, if they're not so crispy,
You're right.
they'll kind of catch a little bit of
Air
sail.
resistance.
Yeah,
Yeah.
I think that's what it is. Anyways,
Learn for next time. $5
go ahead and touch it. Okay, now Sam, right?
Yep.
Okay, go ahead and put your hand there. Yeah, Sam, I'm going to put it with George Washington facing outward towards the students. All right? And the thing about it is, if I do this, see, you're not supposed to dip your hand down there. That's a disqualification. Give me my dollar back. Okay, go ahead,
Try again?
Give me another shot.
All right.
Don't dip your hand down, because that's not, because anybody can do that. All right,
Yeah.
anyways, the whole thing is, are your reaction time, is your reaction time fast enough to close your hand by the time the dollar bill moves from here down to here, before it moves down to here? Because if it's down to here, it's beyond your grasp, because you can't move your hand down. Okay? So if the dollar bill moves this distance before you close your hand, you don't get the dollar bill. Carl's got good reflex. Sam, I don't know. Let's just check. Well, let's give him another shot.
I don't think I'm as good as Carly.
I know it's pretty good. I know, because see, the thing about this is, when you're doing something like that, that was out beyond his reach.
No.
Do over.
You sure?
Yeah, it was.
You sure?
It was way out here.
All right.
Okay. See, I got to drop it right through here, otherwise it's kind of, so it's. This guy over here, Sam.
You beat me.
Right.
You beat me.
Let's give both of them a hand. Well, actually, I got some quarters in my pocket, so I guess I can still write about something like that. Anyways, Sam, thank you, and Carly, thank you. And what you just saw is kind of a homely example of Freefall and your reaction time. And everybody has, some people have quicker reaction times than others. And so if you have fast reaction time, it doesn't have enough time to fall out of your grasp. You can hit it. But if your reaction time is slow, it's only down here by the time you put your hands. And so time and distance, free fall. That's what we're going to tackle today. We're actually going to get to this by the end of lecture when we do the talking PDF. There's some equations and stuff that is really kind of cool. Let's get back to the podcast now. And just so you know, let me get my headset back on here. This demonstration is also available in YouTube in the demonstrations playlist. And actually, the one in YouTube is a few semesters ago with a student that, and he got a $5 bill. And it was, it was my lunch money. So it was a big disaster. But you can, if you want to view the same demonstration, and you're within the sound of my voice, you can look at the demonstrations playlist in my YouTube area. All right, let's get down to some more business. We're going to look at motions in 2 dimensions plus time. And we're going to start with some basic stuff, simple. And then we'll get back to the free $5 Freefall demonstration. We'll kind of get the equations for that going. Maybe we'll get them finished. We didn't quite finish it in morning lecture, but maybe we'll finish it today in lecture. So let's get going with this. I love this picture. This is a FA-18 Hornet, I guess, or a Super Hornet maybe, taken off from an aircraft carrier. All right, so here's our task. We're studying the motion of an object between point A and point B. Boring. But yet, the thing about this is, even the fanciest quantum field theory begins by trying to figure out this particular question in a certain manner that allows for the quantum fields of the nucleus and the electron and so forth. All right, first move, where do we start? Well, let's map it out on graph paper. All right, and I suggest that you use a big piece of paper because or a new page in your notebook if you're taking notes, because we're going to be making notes and calculations and stuff based on this sketch. Okay, I superimposed behind this set of dots here, point A and point B, some graph paper. And let me draw in X and Y axes. Y-axis vertical from the lower left to the upper left. X-axis horizontal from lower left to lower right. Here they're labeled. The Y on the vertical axis up here in the upper left. And X, that's the customary label of the horizontal axis. But you could call it James and Bob if you want. Just don't confuse them. And the other thing you have to do is, all right, your graph paper, what does it stand for? Well, it's going to stand for either meters or maybe miles, kilometers or nanometers. A nanometer is a billionth of a meter, the billionth fraction of a single meter. And by the way, in chapter 1, there's a little blurb about scientific notation and nanometer distances. You might, if you're feeling a little rusty on scientific notation, go ahead and double check that as soon as you get your textbook. By the way, raise your hand if you've gotten the textbook from the bookstore. This is pitiful. But no, they're out. They're out. I asked my other class, how many, there was only about 7. So that means if they've sold 7 or 8 and they're out, that means they must have had about 6. Or it's unbelievable for a class of 600. What are they doing over there? Anybody here work in the well, probably don't want to raise your hand. I should give them a piece of my mind one of these days. One of these days, Anyway, so what we're trying to figure out here is, or what we're trying to decide, depending on what the object is, you might want to use meters or miles or nanometers or some other, light years if you're working in astronomy. But for us, human scale things like this classroom, your dorm room, your car, meters are pretty good. For something like a city, miles or kilometers are pretty good. Something like an atom or a molecule, nanometers are pretty good. So let's just say that this is a human scale system that we're observing in the grand book of the universe. And therefore, we're going to be working in meters. So that means that I can now use the graph paper to figure out coordinates and know what they mean. Okay, point B, 44 meters from the origin to the right, and 24 meters up from the origin. Point B, and then point A, 8 meters to the right of the origin and 16 meters up from the origin. All right. So that's your first thing. Get the coordinates, and you can make the coordinate system anything you want, anything that's convenient. And this one's not too bad. Now let's draw a straight line between the 2 points. Now The most basic thing, if you're studying the motion, you have to know how far it moves from point A to point B. How do you figure that out? Well, use the Pythagorean theorem. Here's a right triangle that goes along the line between point A and point B. Let me park it down here a little bit. All right. So there's the dashed line, and then the right triangle. And the difference in the x-coordinates, 44 minus 8, that's 36. The difference in the y-coordinates is 24 minus 16, that's 8. So your distances on the perpendicular parts of the right triangle are 36 meters horizontally and 8 meters vertically. All right. Now, I didn't, in the coordinate pairs here, 8, 16, I didn't put 8 meters, 16 meters, but if you do, that's fine. I didn't put 44 meters, 24 meters up here in the upper right, but you can if you like. But I do have them down here on the triangle, just to remind me. And a reminder to you is that in the appendix, triangles and other shapes, there's a little bit more instruction about Pythagorean theorem and how it works, why it works, and I'll just recommend that to you for studying as soon as you get your book squared away. Right, you've got it, and I've got the second edition running now, as well. All right, so there's a little bit of extra reading about that. You can actually read the entire appendix if you want. All right, so Pythagorean theorem. Here we go. The distance is the square root of 36 squared plus 8 squared inside the square root sign. So that's a quantity inside the square root sign. All right, be careful about that. You know, that's the old idea, a squared plus b squared equals c squared. All right, so the distance d is the hypotenuse, the length of the hypotenuse. 36 squared, you can verify that. I believe it's 1296. Anybody verify me on that? 1296? Yeah, okay. And then 8 squared, that's easy. That's 64. Okay, so the sum is 1360. Now you do the square root of that. And hey, you guys, start bringing your calculators to class. Get you a calculator. Cell phone is all right, but you're going to need a regular one on the exam, so you may as well get it, start bringing it to class so you know how to use it. Square root of 1360 is 36.9 meters. All right, so that's a little bit bigger than this classroom, I think. But that is an example of one of the very first things that you've got to do if you're studying the motion of an object from point A to point B. All right, let's keep going. Now, I'm going to give you an iClicker question. So get your iClicker out. And we're going to operate in frequency AA. So if you haven't used your iClicker yet in this class, hold the power button down until the until the big square flashes, and then type in A twice, AA. And then you'll get you'll get a check mark and the Go Nitro, and then I think it'll say ready. All right. Anybody get Go Nitro? Raise your hand. Sweet. All right. Now, you guys can click until you've registered in web courses, and hopefully we'll get it working eventually. But until you've registered, I don't know whose clicker is whose. In other words, this little receiver up here, here it is. Here's the antenna. It's kind of worn out. I've been using this for a while. Anyways, this is my receiver, and your clicker is like a little teeny cell phone, very basic. It doesn't transmit voice, and not for a very big distance. It just transmits, clicks and stuff. My receiver picks up two things. Every time you click a letter or something, it picks up the letter and then the serial number of your clicker. So your clicker always sends serial number and whatever you click in. All right. But I don't know whose serial number goes to who until you've registered that serial number in web courses. And that's what that iClicker registration page is supposed to do for us when it works. It's supposed to hook up your iClicker serial number to your NID. And once that's done, then I know whatever you click, I'll know it's you. All right, so that's why you got to register as soon as you can. All right, let's do the question. Calculate the distance okay, calculate the distance between point Q and point C. All right. And it's multiple choice. Now here's what the scoreboard looks like. I don't usually show this, but I have it on my display. It tells me how many seconds have elapsed and how many students have voted. 23, 24, 25, and so on. All right, so go ahead and make a calculation. And then that'll be good. And then decide. Now, on Thursday, we'll do another simple calculation, and you'll type in a number with your iClicker. It works a little differently. But for multiple choice like this, just click the letter A, B, C, D, or E, and it will send automatically. Okay? 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, pretty good. 152. Excuse me. Let me show you. Here's the scoreboard. Most of you voted correctly. The correct answer is E, and most of you got that, so that's good. And there were 158, I think, that answered. Let me show you how to get that answer. If you did miss it, here's how it works. 62 squared plus 92 squared added together, and then square root the lot of it. And that'll give you the distance. Okay, 62 squared, that's 3844. 92 squared, 8464. Add them together and you get 12,308. And then square root that and you get approximately 111. And most of you got that. And just so you know, that's the distance in meters from Qdoba in the Student Union to Chick-fil-A, which I'm getting kind of hungry. I haven't had my lunch yet. I got my snacks and my lunch up here, but I haven't eaten lunch yet, so I'm getting kind of hungry just thinking about that. Anyway, now, I want you to write down what we're about to go through because I want to give you some test-taking skills. You know how they say, well, see if you can, if you're stumped, you don't know the answer, see if you can reject one or two and then make an educated guess on multiple choice. Well, let's look at this and see what basis we have for rejecting some of these other answers. All right, now this one, I think most of you figured this out without too much problem, but let's look at it carefully because there's something you can learn here. First of all, option A, it's too big. Why? Because it's actually the sum of the two perpendicular sides. Now, if you're walking in a city, you know, you're going 62 blocks east and then 92 blocks north in Manhattan. Well, you can't quite do that in Manhattan, but anyways, 62 meters and 92 meters north, then yeah, that's the distance you travel, the sum of those two. But if you go on the hypotenuse, no, that's not what you do. By the same token, or by a similar token, okay, X out, option A. Option B, 30, that's no good. It's too small. And that's because it's the difference between the two perpendicular sides. 92 minus 62, that's no good. All right, the hypotenuse is definitely bigger than that. Matter of fact, the hypotenuse is bigger than 62, and it's bigger than 92. So whatever else you say, for sure the hypotenuse has to be somewhere between 62 and 154. It's going to be smaller than 154, and it's going to be bigger than 62, and actually it's going to be bigger than 92. You can write that down. Now that being the case, if the hypotenuse is got to be between 62 and 154, that X's out this one, option C and option D. Ding, they're out of here. All right? And so that's what you want to do. And then, ching, you get your bonus, or you get your dinero on the test. Now, I'm bringing this up because I want you to understand something about the questions that I write. I hate trick questions. And I hate stupid questions that ask you stupid things. So for instance, I'm not going to ask you a question about the distance from Q to C and then give you these four options: 110.4, 110.7, 111.1, and 111.3. I'm not going to do that. I'm going to give you the correct answer, and then three that if you remember a little bit of a few of the concepts, you'll be able to reject some of the wrong answers. Because if you think about it, a multiple choice test has to have a correct answer, of course, and then it's got to have 2 or 3 or 4 slightly tempting or maybe very tempting but wrong answers. And the way that you want to do that is to be able to sift out the wrong ones and maybe get the right one. In this case, we sifted out all the wrong ones. And so you want to be able to do that. And if you do, to do that, to do this process of rejecting the wrong answers, you've got to think. And I wrote out most of the thinking process. All right? And so on an exam, and everybody in here, you're all going to be caught napping on 1 or 2 at least. And you're going to have to really think, now how can I get this? I've got to choose. Okay, I can eliminate A, and option C is definitely out. But what about option B, D, and E? And you've got to be able to think all your way through, and you will be able to. There's nothing tricky about this. If you remember a little bit about distance formulas, you'll know that there's only one answer that's possible here. You know, so think about it this way. Even if you don't have a calculator, you can figure this one out. I mean, if you can do addition and subtraction, you can figure out A and B are wrong. And if you figure out A and B, then you can eliminate C and D. Then you're left with the one that's right. All right? So you want to be able to do that, and not, we're not going to have hypotenuse questions on the midterm. We're going to have regular physical science questions, but you still are going to want to think. And that, my wonderful student, is going to get you 1 or 2 more points, 3 or 4 more points, maybe even more on each exam. And by the end of the semester, you're going to be looking at a nice grade if you think. All right, let's keep thinking about motion between points A and point B. You know, this line segment we drew, the length of it gives us the distance that the proverbial crow flies from point A straight to point B. But what if the crow doesn't follow a straight line path? You know, what if the crow, or whatever the object is, what if it takes a curvaceous path like that? All right, go ahead and sketch that one in. We've got to be able to handle that, and we will be able to handle that. You can make a note here on a curved path. This one, in addition to having a speed, you've got to turn the steering wheel on this path. If that was you on a road somewhere or on a bicycle somewhere, you'd have to steer with your bike or steer with the steering wheel in your car. And that's part of the motion between point A and B, if that's what's happening. I mean, it might be a straight line path, but it might be curved. Or another one, here, let me park this down here. It might be a segmented path, something like this. That's more like a robot. A robot manufacturing some a computer chip or something like that, they've got to work like this. They don't usually move in graceful curves. All right? They're going to have to work in segmented paths like that. So, that's one of the things that you've got to be able to handle. What kind of a path is it? So it's not just point A and point B. You've got to know what the path is between the 2 points. And then you have to have temporal information. So in other words, for instance, when is it at point A? Right, now let me get these things out of the way here. All right, let's say that it's at point A at 1:22:08 p.m. And let's say that it's at point B at 1:22:47 p.m. So that's T subscript B. Hey, you guys, what's the elapsed time? 73 seconds. What? What's the elapsed time? 39 seconds. It's T subscript B minus T subscript A. The difference in the two. So you have two clock readings, and you subtract them basically. Now, a stopwatch will do it for you, but I mean, if you're using a clock, that's how you do it. But just like they say on infomercials on TV, wait, there's still more. Another thing you have to figure out, does the speed vary along the path? In other words, is it like the tortoise? Smooth and steady and wins the race. Or is it like the hare? Fast, take a nap. Fast, take another nap. Lose the race. That's something that you've got to figure out as well, no matter what kind of path you're on. Does the speed vary at all between the points A and B? So, there's a lot of stuff that we've got to get squared away. So let's make a list. All right, here we go. Positions, mapped out on graph paper of some kind of coordinate system. And then from that, figure out a distance. In meters or in light years or, whatever the distance scale that you're working. We're mostly going to be in meters. Charles. Number 2, times. Your clock readings, and then subtract your clock readings to get an elapsed time. And then you want to know basically the shape of the path. The straight line path, as the proverbial crow flies, that the crow never has to change the steering wheel. He's just kind of cruising down, set it on cruise control and just, straight ahead. But the fuzzy path with the curves, that's continuously changing the steering wheel. And also the speed at each time. So if, for instance, in Freefall, that dollar that fell, that Carly nabbed, long may you reign, Carly. It was starting at 0 velocity. Then I let it go, and it acquired downward velocity, so it was faster at the point that she caught it than it was at the point when I released it. It was 0 when I released it. So let's get down to the business of calculating speeds from distances and from times. Now, here's the main formula. Speed v is delta x over delta t. Now, what is delta x? That's a symbol that we usually use to symbolize the difference. Delta, capital Greek letter delta, capital D for difference, subtraction. XB minus XA, X2 minus X1. The difference in two x coordinates. Or it might be in the numerator, you might have a hypotenuse, if you've got to do Pythagorean theorem. But you've got some kind of a distance up there. And for us, usually we're going to be in meters. For most things. Now, elapsed time, you've also got to have that. That's delta t. The symbol is the difference in the two clock readings. So later minus earlier. Make a note of that. Delta t is later minus earlier. Delta is always the later value minus the earlier value. So delta x is the later x value minus the earlier x value. That's the change in the x coordinate. Delta t, the elapsed time, is the change in the time coordinate, if you want to think of it that way. So for us, it was 39 seconds for the example. Now, speed is the quotient of those two quantities. And we would say that it's an average time rate. And underline the word average because it's not, this is the formula for average but not instantaneous speed. At any instant of time, a moving object will have a speed, but the only way to calculate or estimate that is by making an average speed calculation for a small delta x and small delta t. Anyways, we're going to put the numbers in now for this calculation. So speed the quotient. Here we go. Here's our formula. V equals delta x over delta t. Now let's put our delta x, 36.9, in the numerator and 39 seconds in the denominator. All right, that's not too bad. Raise your hand if you've had calculus class before. Let me see a show of hands. Raise them high. You see that? That's a bunch of yous. You guys see a derivative here? There's a derivative in this. Quotient, calculated. Anybody verify me? 0.946? Raise your hand if you verify. Okay, good. Yeah. 0.946 meters per second is your speed. Now, let me give you a little side note about meters per second. 1 meter per second is approximately 2.25 miles per hour. Let me repeat that. 1 meter per second is approximately 2.2 miles per hour, 2.25 approximately miles per hour. So this is 0.946 meters per second. So that's 2 point something miles per hour. Kind of pokey. If that's you walking, you're just kind of strolling, you know. So it's so that's just a good rule of thumb. And everybody knows about miles per hour and speed, but meters per second is a little bit different. So just remember 2.25 miles per hour for every 1 meter per second of speed. And you know, you can kind of get an idea of how fast something is moving. And of course, you definitely want to have some speed if you're trying to get away from some grizzly bears, especially a grizzly bear mama with a bunch of little baby bears. That is trouble. So you want to make some distance between you and mama bear, mama grizzly there. So let's figure out this whole idea, and this is going to lead us to some sketch work on the document cam to close class today. The distance formula is based on the average speed formula. You know, the average speed, delta x over delta t. If you multiply both sides by delta t, you get delta x equals v delta t. And so if you know the average speed, you can figure out the total distance traveled if you know the elapsed time. And hopefully it'll be enough to get away from. Actually, if you're with a friend, all you have to do is run faster than your friend. So if you're, that's how you survive a grizzly bear. Just run faster than the slowest friend you have. Now, what we're going to do here is use this formula here. Delta x, or distance, is v times delta t. We're going to use that on the document cam, and then I'm going to turn it into a talking PDF after class, maybe tonight. And then we'll do some homework. Now, let me, so we're going to go to the document cam. Caroline, could you come up and help me with this? Just to remind you, the homework one, it'll be activated, I think, at 1:30, right after class, and it will be due Thursday at noon. So let me terminate the